Tiwari, actually also a previous student, a PhD student of mine. He's currently, as you can see on the slides, a postdoctoral fellow at the Odin Institute of Computational Engineering and Sciences at the Department of Physics, University of Texas at Austin. He's also one of the developers of the DFT package Quantum Espresso and also coordinates the sub-package EPW. He holds a dual PhD degree on material science and engineering at Leuven and the University of Texas at Dallas, so Austin or Dallas. And he also obtained his master at the India Institute of Engineering Sciences and Technology, where he was also awarded the Director's Silver Medal. So as you can see, the title, First Principles Modeling of Magnetic Material, is the first of a series of 4 lectures. So we will give 2 lectures on the magnetic part, let's say,
yep.
And then 2 other lectures later on electroforming physics from first principles. So he's here in the context as a visiting scholar for the Erasmus Mundus Master in Nanoscience and Nanotechnology. So I hope that you enjoy the lecture. Thank you.
Thank you, Professor Suri, for a very nice introduction. So, as you already know by now, I'm Sabyasachi. And today I'll talk about the first principles modeling of magnetic materials. First, I'll give you some motivation that why magnets or magnetic materials are interesting. Some recent developments that's happening in magnetic materials in context of devices. And then I'll talk about how we really model them and why, what exactly first principles methods are, and how we exactly model magnets. And eventually I'll conclude with a new kind of a model that we have developed in our own group with Professor Soe. So yeah, the lecture is a bit advanced and requires a bit of prerequisite on some of the things that I'll discuss. For example, some of you would have to know what a band structure is, and a bit about spin Hamiltonians, or at least the energetics. But if you have difficulty in following something, you can just raise your hand and ask me what's that, and I'll try my best to give you an answer. So without wasting much time, so this is the part 1, where I'll just describe the basic theory, and then in the part 2, we will actually do some hands-on calculations, and basically you will be able to see the magnetic switching, the magnetic order, and all those kind of things using a code that we have developed as a freely available package. So yeah, without wasting much time, this is the outlook of my talk. I'll first give you some motivation, magnets and models, ab initio modeling, test cases, and then we will conclude. So motivation, many of you who are from a bit older generation might remember we used to have hard drives like these, which were made up of magnets. These were memory devices. So memory devices in your computer store information, and magnetic devices store information in the spin. So an up spin, something I've shown here, can be state 1, a down spin can be state 0, and then the computer works in binary, so 1, 0 is all you need to store, and that's how your memory devices work, especially when it comes to magnetic memory devices. So magnetic memory devices store information in the magnetization of the material. The device actually that does that, so it's more complicated. It's called the magnetic tunnel junction, and magnetic tunnel junction is basically a device that comprises of 2 layers of magnets. So one layer is called the reference layer, whose magnetization is always fixed, and the top layer is called the free layer, whose magnetization is switched. Now, in a memory, you have to do 2 operations. One is to read what you have actually saved, and one is to write, that you want to save something, you write that. So for the read, depending on the direction of the free layer magnetization, you have a difference in resistance which can be measured. And using that, uh, you can find if the state is 0 or the state is 1. To write, you have to actually change the magnetization of this particular free layer, and there are different methods to do that. One is that you directly inject spin. So you have a material which has a spin difference, and then you inject these electrons which have a particular spin into this free layer. When these electrons are injected, so here you see that when the electron population changes, your spin actually switches. And that's how you can actually change the spin orientation of this free layer, or write. The other method, which is, as you can see, and those of you who have electrical engineering background would know that transferring current always requires more power, because you're basically transferring charge. There is another method of changing the magnetization of this free layer for the right operation, and this is called the spin orbit torque. So you have a material, a class of material which are called the Hall materials. And these materials can be electrically biased. And depending on the direction of the electrical bias, you can actually switch the spin in the Hall material. Now, when the spin in the Hall material changes, it also puts a torque on the free layer, and that's how you actually change the spin. So here you're not really injecting the spin, but rather you're changing the spin by some kind of invisible spin torque kind of a force. Because there is no transfer of charge, and whatever loss you have in the ohmic resistance, SOT type of memories consume less power and are more scalable compared to the STT type of memories. So the first is spin transfer torque, the other one is spin orbit torque. In this talk and even the next talk, we will only be focusing on the spin orbit torque kind of devices, although today's talk will be more focused on the magnetic materials. So without wasting too much time, let's get into the devices. So the Hall material type of devices or the SOT devices, the basic idea is this. You have something kind of a Hall material, or it can be more exotic material like topological insulators. What happens in these materials is that when you inject carriers or when you inject electrons from one direction of this material, for example, left, one of the edges will have a particular spin majority. The other edge will have exactly opposite spin majority. However, when you inject from the other side of the material, the charge carriers, or basically you're changing the bias, the spin majority of these edges changes. So depending on the direction of the bias that you're applying in these materials, you can change the direction of the spin. What next happens is that you can bring a ferromagnet close to this, and these spins which are on the edges of these materials will actually be putting a torque on the ferromagnet and basically changing its spin direction when you want to write. So this is the basic of these devices, and as you can already understand that there is one requirement that comes for the ferromagnet, and the requirement is that its spin direction should be easy to change. So if it is a very hard ferromagnet with a very strong anisotropy, anisotropy is the property of the material that of the magnet that decides how difficult it is to switch its spin direction, this kind of device is not going to work. So you want to have a sweet spot where the magnetic switching is easy in the ferromagnet. This has always been the bottleneck of these kind of devices, so that's why they are not commercialized yet, or they don't exist really in any of your electronic gadgets. However, the recent advances, the reason is because the magnetic materials that we know are mostly hard ferromagnets. Recent advances, however, in the magnetic materials are very interesting. There is something called a layer of two-dimensional materials have been found which can act as magnets. These magnets actually have very low, they have anisotropy, but these are soft magnets. And because these magnets are actually layered, and the interaction between the layers of these materials is van der Waals, it's very easy to interface these materials as well compared to normal magnets, because when you interface to materials, there is some kind of defect that comes in. The only bottleneck with these 2D magnets is that the Curie temperature that they have is very low. So Curie temperature is the temperature at which it's basically the magnet is ordered, below which the magnet is ordered, above which the magnet is disordered. However, recent theoretical calculations or some experiments have also shown that it is possible to realize high temperature 2D magnetic materials, even in exotic systems like doped dilute systems. So the question is, the basic philosophy of research is that basically an experimentalist goes in the lab and grows the material and then says that these are the particular properties, and then they become standard, and then they are used by people who will be designing circuits and all. However, the problem is that when we try to find the materials and when we try to find new materials, we have to grow them. And growing new materials is hard and expensive. There's no guarantee that these materials will ever be grown. And if we look at so that's why the experimentalists have to focus on the most promising materials. If you look at the possibilities of the materials which can act as magnets, and so this is, and if we look at the periodic table, these are all the materials which are basically transition metals. And then these are the materials which are halogens, chalcogens, those kind of extra materials. And combining these two, you can get some of these two-dimensional magnets, or some of these layered two-dimensional or soft magnets. However, because the possibility is pretty large, because these materials can be bivalent, trivalent, pentavalent, experimentalists can't do experiments on all of them and find out which material is the best. So the idea is of theoretical modeling is two-way. One is to understand what's exactly happening in the experiment so that we can optimize the material and the device properties. The other one is to guide the experimentalists to find the best materials. So if I have a method where I don't have to go into the lab, rather I just do some calculation on my computer with with these materials and predict that the particular material is going to be good, that saves a lot of cost and also the time. So for a good theoretical guidance and a good model, it's necessary that it's predictive and it's benchmarked. Predictive in the sense that it doesn't have to predict the exact value of the experiment, but either it's consistently lower than the value which we get in experiments or consistently higher than the value which we get in the experiment by certain percentage, then we assume that the model is good and it has some predictive ability. So now it brings us, so this is exactly what we want to do, is to build models for magnets using which we can predict if a particular material can be a good magnet or not. And then it brings me that what are the existing models and what are the types of magnets that really exist. And this is where I want you to have some prerequisite on the band structure or the band theory. So the first is the type of magnets. So magnetic moment or magnetization is basically the summation of the density multiplied with the Pauli spin matrices. So the density is the density of the electrons. The alpha beta are basically the spin directions, x, y, z, well, the two spin directions. And basically the trace over the density and the Pauli spin matrices gives you the magnetization. Now, as soon as you can see that there is density involved, this would mean that the magnetization will have some dependence on your band structure, right? Because The band structure is basically the representation of your excited and the valence state. So the valence bands are basically the bands which are filled, and the conduction bands are basically the bands which are empty. So the density is only the summation over the filled bands, right? As many electrons you have in the system, that gives you the total density. In the case of insulators, it's pretty easy because the valence bands and the conduction bands have a gap. That's why they are called insulators. So your valence states and the excited states have a gap. In the case of metals, the gap closes, and your valence and the excited states basically do not have a gap, and there is no separation of the valence electrons to the conduction electrons. Based on this difference between the bands, we can differentiate the magnets into two categories. One are basically the localized magnets, which only appear in the insulators generally. The magnetic moment in these kind of magnets is localized on the atoms. It's a property that comes from the valence band electrons, and these are the only magnets which can be described by a model that I'll discuss later, which we call as the Heisenberg model. The other type of magnets are basically the magnets where you have these bands which touch each other or even cross. These are metals. And because in the metal there is no separation between the valence and the conduction states, the magnetization arises due to the conduction electrons. It's more difficult to model these systems. So how exactly do localized magnets and the itinerant magnets behave if I have some way to look at them atomistically? And we do. We now have experimental methods which we call the magnetic force microscopy, where we can even look at the spin orientation of each of the atoms. So in the case of localized magnets, below the ordering temperature, the spins are oriented and ordered. Above the ordering temperature, the magnetic moment on these atoms is still there, but it's randomly distributed. In the case of itinerant magnets, what happens is that below the critical temperature you have ordered, but above the critical temperature, the magnetic moment itself on the atoms starts diminishing. So if I have a way to look at the magnetic moment in these magnets, in case of localized magnets above the critical temperature, I'll still find some kind of magnetic moment on each of the atoms. While in the case of itinerant magnets, I'll find absolutely nothing above the critical temperature. In this talk and also the next talks, we will only focus on the localized magnets, which are interesting in terms of applications. So again, localized magnets have many versions, like there are many types of localized magnets, but the two which are depending on the low temperature order are ferromagnets, where all the spins are oriented in one direction, and antiferromagnets, where you have spins oriented but in opposite direction. Well, this is a hexagonal lattice, so it's more complicated, but you get the point. And then you have paramagnets, where you have these magnetic moments, but they are randomly oriented. The ferromagnetic and the antiferromagnetic states, so this is basically comprise what we call as the ordered state. So there is order, long range order, while the paramagnetic state is basically a disordered state. And when we increase the temperature from the ordered state to disordered state, we basically go from the ferromagnetic or the antiferromagnetic state to the paramagnetic state. However, this transition doesn't happen smoothly. Rather, it happens abruptly at something which we call critical temperature. For the case of ferromagnets, this critical temperature is called the Curie temperature. For the case of antiferromagnets, this critical temperature is called the Néel temperature. Above this temperature, you have disordered state. Below this temperature, you have ordered state. This is a parameter that we want to obtain from our models, because for devices to operate, we need to operate these devices at room temperature, and A good magnet should be having a critical temperature above the room temperature, at least a couple of hundreds. All right. So how do we model magnets? So one of the oldest models is which still works is the Heisenberg's model, where you model the energy of the magnetic system using a Hamiltonian that looks something like this, where the first is the nearest neighbor exchange. The second term is the next nearest neighbor exchange. You can extend it up to the as many as many neighbors as you want. And then the system likes to be at the lowest energy. And if I look at just two spins, then if the spins are oriented in one direction or the same direction, if you just look at this equation, your energy will be minus J. If they are oriented in the opposite direction, the energy will be plus J. These spins are dependent on the temperature, so depending on the sign of this J, you can have either a ferromagnetic state as the most stable state or an antiferromagnetic state as the most stable state. So it all boils down to, because these spins are dependent on temperature, it all boils down to solving this model as a function of temperature and finding out that at what temperature exactly I start seeing order in the magnetic system. And above that temperature, I see disorder. And it all boils down to obtaining this exchange parameter because that's all that we need. So once we have this exchange parameter, we can plug in the spins, and then we can change the spin as a function of temperature, and we can solve the Heisenberg Hamiltonian and find out which is the ground state of the system, as well as at what temperature does this ordered state appears. The problem with this method is it has been applied in some cases and it doesn't work. And for example, in the case of a material, it's chromium iodide, its experimental Curie temperature is far below than what is predicted by this model. And in another system, it's also far below chromium telluride than what is predicted by this model. So what is really lacking? So magnets also have one more funny property, which we call anisotropy. So the magnetic moments, so for example, here is an example of a ferromagnet. All the spins are oriented in the outer plane direction. This has certain energy. But these spins, this is also a ferromagnet, but the spins are oriented in the in-plane direction. So basically, the spin axis of the entire system is changing. Ideally, there should be there should be invariance with respect to the axis. But in the case of magnets, this invariance is broken. And there is a difference between the energy of these two states. And certain materials like to be in one of these states. So all these spins aligned in outer plane direction, all of these spins aligned in the in-plane direction. And this is what we call as the anisotropic energy. And this is something that we need to take into account in our model as well. So as you can see, that the spins are no more up and down simply, but they can actually be a float number, or basically they are vectors which can take directions. So we have to modify the Heisenberg Hamiltonian, which we do. So instead of writing the Hamiltonian as just a scalar, we basically convert the energy, the Hamiltonian, into a vector. So the first term is actually the exchange term, where you have spins, which are vectors. And the exchange interaction, which was just a number, now becomes a tensor. The second term is basically what we call as the on-site anisotropy. So if you have all the spins that like to be in the outer plane direction, here we call it Z, there is no energy penalty. But if they like to be, but if you change the spin direction, there will be energy penalty. So basically, this term ensures that all your spins are in the preferred direction of their anisotropy. This is another effect. Also, the anisotropy is also accounted in the exchange tensor. We can also convert these exchange tensors, so these are discrete numbers, but then I can model the system as a continuous system and convert these exchange tensors as just a function of distance. So in the real space, they become function of distance. In the space of their magnetic orientation, they are still tensors. Is this point clear? Any question? Okay. So the goal is actually to determine these exchange parameters some way if I have some method from which I can determine these exchange parameters. And these exchange parameters should be determined without any input from the experiments, because that's the point. We want to predict what's going to happen in the experiment, so we don't need any input from them. We need to account for the full anisotropy. And once we have all these things, we need to solve the Heisenberg-Hamiltonian. So at this point, I have already built the Heisenberg-Hamiltonian, and I want to solve it to determine the critical temperature, as well as to do the magnetization dynamics. So we need some reliable method to obtain the total energy for spin configurations. And that's where the ab initio modeling comes into picture. So without going too much into the details of the density functional theory or ab initio modeling, the density functional theory is basically has been the workhorse for the ab initio modeling of materials. We can discuss this, and if you have questions, we can talk more. But what we actually do in the density functional theory is that we represent the total energy of the system as a functional of the density. This density, so if you write the Schrödinger equation, you'll find out that it has many terms. Basically, we assume we take an approximation of the single, so we take the single particle approximation, and particle-particle correlation is basically taken as an approximation, is taken into account using the density of the electrons. So that's what our density functional theory is. And this density is solved self-consistently with the external potential, which is, and the density is obtained by solving these Kohn-Sham equation or the Schrödinger's equation. All you need to know is that this theory is based on the variational principle, so you keep minimizing the energy and try to find out the best approximation for your, try to find out the best wave functions that describe that particular system. This always ensures local minima. We can do constrained calculations. So basically we can give spin orientation and find out the total energy of that particular spin state. And that's all that we need. So we need to find out the total energy of the spin states, and we need to find out without any kind of experimental input. And that's where the density functional theory comes into help. This is a bit more involved slide, but basically DFT can be both collinear. So the spins actually do not talk to each other. So in the beginning that I said, the Heisenberg-Hamiltonian, the way it was. And it can also be what we call non-collinear. When you have spin-orbit coupling in the system, your spins will actually can talk to each other, and this is the effect that gives rise to anisotropy. So basically we can give three-dimensional spin vectors as the inputs and calculate the total energy of that particular system using DFT. So now we have a method of obtaining the total energy from the first principles, and we already know that we want to model the magnets using the Heisenberg-Hamiltonian. Now the question becomes, how do we bring these two together? And one method that is useful, that has been used for many years, is the energy mapping method. So you calculate the energy of these systems, all spin up, all spin down, you subtract the energy, and then you get the difference between the energy of these two states. You can directly map it onto the Heisenberg-Hamiltonian, as I said, that you can just plug in the values of the spin Si as j, and then determine the j1 from the delta E. Right? It's just a set of linear equations. The problem is there is a set of linear equations, so it will always give you some parameter. And even in the case of itinerant systems, which cannot be described by the Heisenberg Hamiltonian, this method still gives you some numbers. And that leads to misconception, not misconception, but miscalculation of the critical temperature, because itinerant magnets cannot be modeled using the Heisenberg Hamiltonian. So when we use this previous method, and this is exactly the same slide that I showed previously, we actually run into problem. First problem that we run into is that because there are not enough configurations, even this method models the itinerant magnets and gives results which are far off from the experiments. And in the materials which can be modeled using the Heisenberg Hamiltonian, because it doesn't have an isotropy, we basically obtain very different values compared to the experiments. So this is the method that we proposed, and it's kind of now pretty well used, is the method of interaction spheres. It's a bit involved, and if you have questions, try to just ask me. What we do differently is that instead of just the number of configurations, as many parameters you have, we do more number of configurations or configurations inside a supercell of the material and an interaction sphere. We do all the configurations which are allowed by the symmetry, and then we calculate the total energy of all these configurations from the density functional theory. We subtract the total energy of these spin configurations from their non-magnetic counterpart, and we directly compare the Heisenberg Hamiltonian. So the difference is, instead of taking the difference between these different energy, these different spin states and their energies, we do all these spin states that are possible and then map them directly onto the Heisenberg Hamiltonian. So what we do, we start with the crystal structure, we generate all these configurations inside the sphere, and then we calculate the total energy of the system using the density functional theory of these magnetic configurations, and then we build the Heisenberg Hamiltonian. The issue is that because we have more configurations than the number of parameters that we want to obtain, this is actually an optimization problem. So we basically have to optimize the exchange parameters rather than directly obtaining them, unlike in the previous case where you can just invert a determinant and obtain those parameters. All right, and of course we have to do periodic boundary conditions because we are still at the DFT level. However, periodic boundary condition introduces, this is a bit more involved thing, but it's called the self-interaction. And this is something, so basically when you have periodic systems, you will have interaction between these two images. And these interactions are basically spurious because in a real system you don't have image. So these needs to be removed, and we basically remove that. So this is what we call as the objective function. So here you have the energy that we have obtained from the DFT minus the non-magnetic energy. And then this is the Heisenberg Hamiltonian obtained for that particular spin state and the self energy. And then we basically minimize this objective function or functional. And that gives us eventually the parameters. So the idea is this: we start with many of these magnetic configuration, we calculate total energy, we build the classical Heisenberg Hamiltonian for the spin configuration, we compare the objective function, we compare these energies using the objective function. If the objective function has reached the minima, we go ahead and build the classical Heisenberg Hamiltonian, otherwise we update the exchange parameters. One benefit of this method, which comes for free, is that if your material is not a Heisenberg Hamiltonian, you will never be able to minimize this objective function. And this method, of course, has been used to model many magnetic material which is localized with full anisotropy. Now comes the challenging part, which is the solving the Heisenberg-Hamilton. Oh, yeah, sure. What is an objective function? That's a good question. So basically, objective function is kind of the minimizer. It's it's a function that you define at the beginning. So it's basically nothing but the difference between the energy that you have obtained from the Heisenberg Hamiltonian and the energy that you obtain from the DFT. So this is basically linear regression. And you try to find out the parameter that minimizes the error between these two energies. And once you have that, that means that your Heisenberg Hamiltonian or whatever that you have built is in a good match with your expected value, or basically your total energy that you're obtaining from DFT. Thank you. More questions? No? So now comes solving the Heisenberg Hamiltonian. So when we were building the Heisenberg Hamiltonian, we were all into the classical picture. And there are various ways of solving the Heisenberg Hamiltonian as a function of temperature itself. One we call as the Green's function method, which is the quantum picture. So basically you obtain the parameters assuming that the Heisenberg Hamiltonian is classical, but then you solve the Heisenberg Hamiltonian with a quantum picture. So you basically assume that the spins, when you were determining the parameters, were actually just numbers. But when you do a solution, you assume that the spins are operators. In the case of Monte Carlo or classical solution, you assume that your Heisenberg Hamiltonian is classical all across. And then there is a third way method, which we call renormalized spin wave, which is kind of a bit, what I would say, different from these two, is that you assume that that your spins are basically bosons. That's not true. Spins are not bosons. They are kind of combination, depending on what you're looking at. We can discuss more if you are interested. But yeah, these are the three standard methods of solving the Heisenberg Hamiltonian with temperature. And the end product of these three methods is the critical temperature. So first we come to the Monte Carlo method, which has been very successful. In the Monte Carlo method, what you do is that you assume that your spins are classical. So you start with a random orientation of your spin states, and then if you focus on this blue state, we just rotate that one. This particular state has an energy, and the other state, when we have rotated this, has another energy. If this energy is below this energy, then of course the system likes to be in the lower energy and we accept this solution. If this energy is greater than the other energy, then we basically choose this state depending on the probability, which is basically a function of temperature. So at higher temperature, you will be choosing all the random states because your probability will always be very low, very high. On the other hand, at lower temperatures, you will be choosing less number of these states because your exponential becomes very small. So the probabilities become small. And if we have chosen a state or rejected a state, we keep repeating this until we reach something what we call as the as a stabilization in the Monte Carlo calculation. Once we have done enough steps for a particular temperature and we are happy with the final solution, we do what we call as the ensemble averaging. So we basically obtain the observables by averaging over all the Monte Carlo steps that we have performed, and to find out what is the ensemble average of this value. And this is an observable. So for example, here we are calculating the magnetization as an ensemble average. So we are summing over the magnetization that we obtain from in each of these Monte Carlo steps, and then we divide by the number of Monte Carlo steps. This is a classical approximation, as you can see. The second one is the Green's function method. As I said earlier, you assume that your spins are operators, and then this is a bit complicated, requires quite a lot of discussion, but the central idea is that you convert these spins into ladder operators. And then once you have converted these spins into ladder operators, you can basically use the Green's function equation of motion. You just take a derivative of your spin state and then define the Green's function. And once you have the Green's function equation of motion, those of you who have some background in physics would know that the Green's function equation of motion will actually create kind of an infinite series. We cannot solve the infinite series, but we can truncate the infinite series using what we call as a Tablikov decoupling. This is again requires far more discussion, but this is actually an exact method of solving Green's function, of solving Heisenberg Hamiltonian in the first order. Good. A third method is the renormalized spin waves. So as I said earlier that we basically convert these spins using the hydrogenic orbitals and basically assume that these spins, we do what we call as the Holstein-Primakov transformation and represent these spin ladder states, spin ladders using the bosonic creation and annihilation operators. So these A's are basically bosonic creation and annihilation operators. You can just put these into the Heisenberg Hamiltonian, and then you will get a gigantic expression which will have 4 and 6 orders of and even longer order, larger orders of boson interaction. What you do, you really cannot solve it because then it becomes a non-linear problem, and computers only like linear problems. So you assume that these higher order interactions are represented by the density. So basically you assume that A dagger A is your density, and then you solve, you renormalize your Hamiltonian of the first order with this density. So eventually, if you carry on deriving your Hamiltonian in this fashion, you will arrive at an expression which looks something like this, where you have H naught K, which is your linear Hamiltonian, which is renormalized by this density, S is the spin. And once you have the Hamiltonian described in certain way, you can always write your spin as a function of temperature, and this would give you the ordering temperature. So with temperature, you can see how your spin changes, and if it changes abruptly at a particular temperature, that's basically your critical temperature or Curie temperature. Okay. Yeah, I know it's too much to take. You can compare these methods also, and when we compare models, what we do is that we take one particular parameter, which we call as the test parameter, and against which we compare all these three models, or whatever model you want to compare. And here what we compare is the critical temperature, which is predicted by these methods as a function of the nearest neighbor anisotropy. The central result of this thing is that the Green's function and the Monte Carlo interchange their prediction of the critical temperature. So Green's function and Monte Carlo could be overestimating with reference to each other. There is no real solution that we can compare that if Green's function is better or Monte Carlo is better. So with respect to each other, they will be overestimating the critical temperature depending on the anisotropy. However, renormalized spin wave always underestimates the critical temperature with respect to the Green's function and the Monte Carlo methods. All right, so with this, we next move into results. So What I presented up until now is a method to model magnets where we take into account the spins as vectors and the full exchange interaction. And now we want to benchmark like how good this method is compared to the experimental data. Like that's what we really care about, right? And to benchmark, we want to apply these methods on materials that already exist and who have been tested. And one of the materials is, or the family of materials are these 2D chromium compounds, chromium iodide, bromide, telluride. Their experimental critical components are also known. And here you can see that our prediction matches extremely well with the experiments, which is kind of um, which kind of says that the model works pretty well. The next thing is the Curie temperature. So all these three are basically ferromagnets. And if we look at the Curie temperature that is predicted by the method that I showed you compared to experiments, we always lie within the 30% error. So we make some error, but it's consistent. And in some cases, the error is way below. Now, as I told you that there are three methods of solving Heisenberg Hamiltonian, like the Monte Carlo, Green's function, and the renormalized spin wave. When we compare these three to experiments, we find that, of course, they give you different results for the same Heisenberg Hamiltonian. However, the Curie temperature always lies within the limits set by these three methods. So if you're particular about like what's really gonna be my Curie temperature, the range, one should try to calculate it using all these three methods rather than just trying to be doing one. So yeah, I think I'm on time, and that brings me to conclusion. I showed you how we obtain Heisenberg Hamiltonian, how we build it from the ab initio density functional theory calculations. In all these results that I've shown you, or in this model, we don't take anything from the experiments as input. So everything is just done inside the computer, per se. We show that the prediction of the Curie temperature is quite accurate for the test cases. And something that I didn't show, probably you can talk to me, that magnetism can also be obtained in materials by adding transition metals. So for example, if you have a material which is non-magnetic, you add some transition metal, you can actually make the material magnetic. And those kind of systems can also be modeled on the same line, although they are more complicated. And we can discuss if any of you are interested in learning more about those. So that concludes the part one, where I showed you the basic that goes into the building Heisenberg Hamiltonian. In the next part, we will do some calculations on hand. We will see some simulations, and I'll introduce a package called MagnaPi. So yeah, that's all. If you have any questions, let me know. So I think the first question is like how close we do Curie temperature prediction. Is that? Okay, so what we expect from the Curie temperature for application. So Curie temperature should always be for applications ideally above room temperature. So you want the Curie temperatures, well, you want it above room temperature, but you want it a bit more higher than the room temperature, at least couple of hundred more, because your device temperature can be higher than your outside temperature. So that's the thing. So we still don't have a material which has room temperature Curie temperature, which is 2D magnet. So that's what we want to find. The second question is that if the range is 30%, is that really gonna impact the prediction? Because like for example, we want 300 Kelvin, and if it is like 270 or 330, does that make a difference? The answer is no, because I want the Curie temperature for any kind of application to be above 500. So ideally, I mean, so that's really not the bottleneck. And when we know that a model is accurate, but it has kind of an error bar of 30% or 20% in certain cases, we can be sure of the model that if I should put my money on the particular material that it's predicting to have a higher temperature or not. So very good question. The reason is because it's the spin-spin correlation that is underestimated in the renormalized spin wave, because in the renormalized spin wave, the spin-spin correlation is estimated by a density. So that's what leads to prediction of higher, lower critical temperature. This is actually, I showed you results. The test case is for bulk as well as, so you can see there is bulk and then there is single layer. Yeah, the difference in the band structure is taken into account in the exchange parameters. The spin-spin interaction is independent of the it is depends because it depends on the exchange, but the spins are basically sort of independent of the constraint. So. Mhm. So spins are considered like boson because in the case of Holstein-Primakov transformation, you basically put these spin ladders as a function of bosonic operators. Oh, this comes from the hydrogenic model. So if you this is just well. So if you solve the two-body problem, you will come down to spin quantum number, and that is exactly what is put as the spin ladder operator. So it's a hand wavy kind of approximation that is done. So that's why it's called kind of this is sort of an approximation where you just assume where you take a model which is for the two-body problem and then you use it for the many-body. So that's why. And coming to bosons, or if there is any intuitive picture for that, the answer is kind of no, because spins behave both like fermions and bosons. So. Different levels of theory. DFT and coupled cluster DFT. Okay, Hartree-Fock. Not really for the magnets. Not really for the magnets. And coupled cluster. Well, the coupled clusters are generally used for molecules. So in the case of crystal, if you want to use the coupled cluster, you have extra things like K-grid. So you have a wave vector as well. In the case of molecules, it's very simple because you just have molecules and then the states that they have coming from the orbitals. So that's where the coupled cluster can be used. And basically, in the coupled cluster, you can go beyond first order perturbation, second order perturbation, and those kind of things. In the case of crystals, it's not really that simple. On other crystal, so the thing is that we were benchmarking our calculations. We have done calculations on other crystals, but there are no experiments to really compare to. And there are systems which have been predicted to have a higher Curie temperature, but those are itinerant systems, or they become itinerant, the complications become more, like they become charge density wave and those kind of stuff. So those things we have not really tried with this because those are harder systems to model. Very good questions. That's a good future idea for me to work on. But I think yes. I mean, machine learning is well. I'm not really an expert in that, so I really don't know if that would be easy or hard. But yeah, could be something to look into. Yeah, yeah, yeah. Mhm. Yeah, yeah, of course. So if we want to really have a high Curie temperature material, we should actually be at in this range where we have a very strong anisotropy, and at the same time we should also have a very strong exchange interaction. So ideally we should be operating in this kind of a range of parameters. So that's why we do these parametric studies, and unfortunately we actually fall in this range. So we have a long way to go. Hmm. Yeah. So there are these materials like the iron germanium telluride or MnPs3 manganese. So generally, period 4 transition metals are one of the good candidates. But for 2D, it's always the question boils down to how you really grow it. So it's not really that we don't know where it can exist. It can exist in these set of materials, but the problem is really the growth. Mhm.